here. Now we will solve some examples. First, xn is equal to a to the power n minus 1b plus summation I from 2 to n a to the power n minus I times fi. Solving this by backward substitution. If a is 1, so if a is 1, so this is basically, the first term is basically b, okay? B plus, and inside also we have the term is basically fi, okay? I from 2 to n fi. If and if fn is 1, then we can say that xn is equal to b plus summation I from 2 to n 1, which is basically b plus n minus 1, and this is obviously theta n, okay? So this is one special case. Another special case is if a is 1 and fn is log n, then what we have is xn is equal to b plus summation. Okay. Kaldırırken bir şeyleri bozuyorum genelde. Biliyorsunuz sanırım. Kamerayı da kapatıyorum. B plus summation I from 2 to n log I. So this is what? This is b plus logarithm of n factorial, right? Because log 1 is 0. So we could have added, it doesn't matter, it could be from summation 1 to n, it doesn't matter, it's the same thing. So it's basically logarithm n factorial. Logarithm n factorial is logarithm n times n minus 1 times blah, blah, blah, which is log n plus log n minus 1, which is exactly equal to this summation. So the theta location, theta for this is theta log n, right? Logarithm n plus something. Sorry, theta n log n. Why? Because I have n terms here. This is like log n plus log n minus 1 plus log n minus 2, right? So there are n terms, and the upper bound for each of them is log n. So n terms each with log n, that makes theta n log n, okay? So, so if n is not a power of 2, power of b, we will obtain something like a times x floor of n over b plus something like that, okay? So assume that n is b to the power k. If n is b to the power k, then xn is equal to a to the power k c plus summation I from 0 to k minus 1 a to the power I times f n over b to the power I. So again, it depends on this fn function, okay? So this is another case. If Fn is d, some constant, then Xn is a to the power k times c plus d times summation I from 0 to k minus 1, a to the power I, right? If Fn is some constant. So a to the power k is equal to a to the power log bn. So this is equal to b to the power, a little bit of logarithmic manipulation, log b a to the power log bn. Okay, so that makes, we can change the powers, b to the power log bn to the power log ba. It doesn't matter. So a to the power k is equal to n to the power log ba. So that means that xn is equal to n to the power log ba times c plus d times n to the power log ba minus 1 over a minus 1. So this is n to the power log ba in parentheses c plus d over a plus 1 minus d over a minus 1. Sorry, this is minus 1 also. This is also minus. So because the minus term is not important, this is equal to theta n to the power log ba. Okay? Yana kaydırmak istiyorum ama bunları yana kaydırmaya çalışırken başka bir şeyler oldu. Aşağıda dursun istemiyorum. Ya sanırım yana ya da şuraya geliyordu da yanlışlıkla yaptım onu. Bir daha da reproduce edemiyorum. Neyse, tamam.
Hocam tabletten sesi kapatıp bilgisayardan açsanız belki.
O zaman da benim sesim buradan tam gitmiyor ya. Deneyebiliriz aslında ama yok, onunla ilgisi yok onun ya Barın.
Bilgisayar algılıyor sesini.
Anladım, olabilir. Olabilir. O zaman da bilgisayar algılayacak. Bilgisayardan açacağım. Ama buradan açalım. Anladım. Neyse boş ver, karıştırmayalım. Sonra setup bozuluyor, daha kötü oluyor. So if a is equal to 1, then xn is equal to c plus d times k. That is equal to c plus d times log bn. That is equal to theta log n. Okay. So in merge sort, Fn is not a constant. So this is not the case for merge sort, for example. That's why merge sort is not log n, it's n log n. Okay. So if Fn is if Fn is d times n, then xn is equal to a to the power k times c plus summation I from 0 to k minus 1, a to the power I times d times n over b to the power I. This is equal to a to the power k times c plus d times n times summation I from 0 to k minus 1, a over b to the power I. Okay? So if a is not equal to b, then n to the power log BA times C plus dn times A over B to the power K minus 1 over A over B minus 1 is equal to n to the power log BA times C plus, again, some manipulations, n to the power log BA minus 1, okay, sorry, over n minus 1 over A over B minus 1. So that is equal to n to the power log BA times C plus D times n to the power log BA minus n over A over B minus 1. This is n to the power log BA times C plus D over A over B minus 1 minus dn over A over B minus 1. So this is minus 1. So if A is greater than B, then xn okay, xn is theta n to the power log BA. If A is less than B, then xn is theta n. Okay? If A is equal to B, then xn equal to n to the power log BA times C plus dn times summation I from 0 to k minus 1, 1 is equal to Cn plus dn times k. So it's equal to Cn plus dn times log Bn, and that is theta n log n, which is the case for merge sort, for example. Okay? So we have obtained these results only for specific inputs. By the way, you obtained the message on the midterm, right? It's 2 weeks later. It's on Teams. We have obtained these results only for n, for some specific input where n is b to the power k, okay? So, however, since all these functions are theta invariant, remember the definition of theta invariant, I'm not going to iterate it here, and non-decreasing, we can generalize these results for all n, which brings us to master theorem, okay? So master theorem is the following, and we will use it frequent, and many of the things that we made the derivations of can be implied by the master theorem immediately, okay? Some of them. So let xn be an eventually non-decreasing function that satisfies the recurrence relation a times x n over b plus fn, where n is b to the power k, k from 1 to x1 is c, where a is at least 1, b is at least 2, and c is positive, okay? C is greater than 0. If we are given this, then if fn, so it all depends on what we have in the fn function, okay? That's the only difference. Otherwise, all of them are the same. So if fn is theta n to the power d, where d is at least 0, then we can say the following, okay? Xn is, so we have three possibilities: theta n to the power d, if a is less than b to the power d, and it's theta n to the power d times log n, if a is b to the power d for all n, okay? And it's theta n to the power log ba if a is greater than b to the power d, okay? This is what the master theorem tells us. So if in fact it's a generalization of our previous analysis that we have already made previously, okay, let's write that also. In fact, so the proof of the master theorem can be deduced from our previous analysis. Okay, this is what can be done. So we will now okay, we will not do, okay, a little bit of depth first search. So this is you can see that, for instance, in quicksort and merge sort, for example, this fn is actually theta n, because the merging part we do in linear time, and also in quicksort, okay? So this fn is actually n, which means d is equal to 1. So it is it like, it's actually 2 times x n over 2 plus n, right? With merge sort, because we divide it into 2 and we do the same thing on the both parts. And this is true for a quick sort also, because and then fn is n, because we do the merging step in linear time always, in each iteration, in each recursive step. So in that case, for instance, a is equal to b, and is equal to 2. So both a and b are equal to 2. So if a and b are equal to 2, and this fn is d, so d is equal to 1, right? Because it's theta n. A is equal to 2, B is equal to 2, and D is equal to 1, it means what? A is 2, B is 2, D is 1. It's actually A is B to the power D, this part, right? It falls into this category because A is B to the power T. 2 is 2 to the power of 1, okay? So that's why it becomes, since D is 1, it becomes theta and log n, or merge sort, okay? So this master theorem immediately gives us the result here, okay? By its recursive formula, by using its recursive formula. So now I will start with the analysis of quicksort. So we will finish the analysis of quicksort, and then we will look briefly at breadth first search and depth first search, which you are already familiar with from data structures, but we will just review what you will have, you saw them. And then we will start the second part of the course, which is the design of algorithms. Right now, we are still given an algorithm and we are trying to analyze it. Okay, so quicksort was invented by a student in the time, who then became very famous, not only because of his work on quicksort, but for others in operating systems also. I think he had some inventions. Invented by Hoare in 1960s, who was a very young student and working on a machine translation project at the time. I think British, I'm not sure. So the main procedure, I'm writing the pseudocode also for you to remember. Procedure quicksort. L low to high. Okay. So I have a low index and then a high index because I'm operating on a list L. And I have this low pointer and high pointer, so to speak. Low, high. If high is greater than low, then call rearrange. And we will see what we do in rearrange. L low, high. With respect to a position, which is pointed to by here, like the position, okay? So we divide it basically into two, this position, and then we call quicksort. This position is the pivot, okay? The pivot element, we say its position here. We call quicksort. So this rearrange basically groups them into two, categorizes them into two, in such a way that all the elements that are at most the value of the position of the element that is pointed to by the position pointer or the pivot are in the first half, and the ones that are greater than that are in the second half. But these first half is not sorted within each other, but we just know that their values are less than or equal to the values of the pivot, but it doesn't have to be sorted within itself. And same thing for the other half. And then we continue sorting this not necessarily sorted part recursively, this half, okay? We call quicksort recursively, this time with L low, from low to position -1. And then we call quicksort L position +1 to high, okay? And if, and end. Okay. So what we do is, like, again, we have this low index and high index, and we have this pivot here, and we continue, and there are 2 pointers. One of them is the right pointer, which goes to the right, and the left pointer, which goes to the left. So we continue until they coincide with each other, okay? We continue until these 2 pointers coincide. So one of the elements in the list is selected as the pivot element. So how is this pivot selected? Well, the analysis of the algorithm in general, theoretically, does not depend on how the pivot is selected. It could be the first element, you can take the median one, you can take it randomly, but many practical implementations have been considered, and it was found out that in practice, I think the one that performs best is selecting it as the median, okay? But to find which one is the median, you remember the definition of median, then you need to make a linear search of all the elements. So that makes, but it doesn't dominate the entire complexity of quick sort, which is n log n, okay? So that's why you can select it as the median. It doesn't change the overall complexity. But of course, in practice, picking it randomly or just the first element would save you some constant amount of time. But in general, that was found out. But that's just the one that is in practice that was found. Theoretically, it's still n log n in both cases, okay? So it doesn't really matter as far as this class is concerned, and also in general. So let's write the pseudocode, okay? So the proper position of the pivot is selected, and then quicksort is called recursively. So before doing that, we need to do this rearrange, okay? How do we rearrange the positions, the elements, with respect to the value of the element pointed to by the pivot, okay? The ones that are less than, and we should be able to do that in linear time, and we will be, okay? So procedure, there are many ways. I mean, there are, at least I know of multiple ways of doing this in linear time. Basically the same mentality, but the algorithms implementation wise are a little bit different, and we will see in the second part of this course the second implementation as well. Procedure rearrange L from low to high, and then position finds the proper position of the pivot element. Okay, I'm not going to write that. Okay, right is equal to low means that the right pointer starts from the leftmost index, okay? And left is high plus 1. Of course, it doesn't high, I mean, the last index is high, so left initially does not point to anything, but its value is high plus 1 means that left starts from the rightmost position. It will, okay? So X is L low, okay? So X is the pivot element. Now in this implementation, we say that the the first element is the pivot, okay? It doesn't matter, but we will just write its value in the variable x. So even if it were the median, it wouldn't change. It would be something like find median, x is equal to find median, okay? So in this, because it doesn't matter, we just say that, okay, it's the first element, the pivot, x is LO. So the important part is this recursion here. While right is less than left, do the following, which I haven't done yet. It means right is less than left means that as long as they don't coincide, proceed, okay? So they shouldn't coincide. While right is less than left, repeat the following. Repeat right is equal to right plus 1. So the right index goes to the right continuously until it finds an element that is greater than or equal to x. Because if it finds an element that is greater than or equal to x, then, okay, there is something wrong here. I'm trying to do my rearrange such that the first half is less than or equal to less than x, okay? If it hits some value that is at least x, then I should stop there because the other pointer will come from right to left. And once it finds something that is also out of order, let's say, this time the opposite that is less than x, then once two pointers stop, then all they need to do is to swap, okay? So that will make things in order, and then they can continue, okay? Until L right is greater than or equal to x. So the left pointer will also go. Repeat left is equal to left plus 1. Sorry, left minus 1. Because it goes from right to left, its value decreases. Left minus 1 continuously until it hits a value that is less than or equal to x, okay? So the equality also we stop, okay? Just in case. If they are equal, we can also, I mean, we will see that we're already done there. So we repeat there. If both have stopped, then I arrive at this if condition, okay? Repeat until this, so I stop, and repeat until that, so I stop. Now both have stopped. If right is less than left, then, so it means I haven't coincided yet. Still right is on the left part and left is on the right part. We haven't coincided yet. We haven't crossed each other yet. So now we can exchange our elements, okay? Then interchange. Where I basically do a swap. L left and L right, okay? And if, and then and while. So if right is greater than or equal to left, then I don't do anything. And we will see why we don't do anything here and still, we don't do anything in that case and still everything is fine. We will show that if such a case occurs, then it means I'm already done, okay? The list is already as I want it to be. It's already rearranged, not sorted yet, because it will be taken care of by the recursion, but the rearranged part is there. But it's very important because what does recursion mean? In each recursion, I will call this rearrange. So I will always be doing this rearrange part. So how many recursions I will have? I will have log n number of recursions, right? Because I'm dividing the list into 2 in log n steps. And in each step, I make this rearrange, which is n. So that's why basically, very roughly, that's why it's n log n. Okay. And now we will take a break, okay, for 10 minutes. I'm not finishing the online course. Maybe I will stop the screen sharing, okay? Online class also, see you in 10 minutes.
Hocam kaydı durdurmayalım yoksa problem olabiliyor
Yok,
bazen.
durdurmuyorum ben. Screen
Tamam.
sharing'i durduruyorum. Çünkü uzun süre bekleyince o kendisi saçmalıyor, zaten durduruyor otomatik.
Tamamdır.
Kaydı durdurmuyorum. Derse devam ediyorum. Sadece ekran paylaşı da şu anda durduramıyorum nedense. Ha tamam, sunuyu durdur diyorum sadece, tamam mı? Mikrofonu kapatıyorum. Görüşürüz. Sesim geliyor mu?
Evet hocam.
Tamamdır.
Geliyor hocam.
Tamamdır. Şimdi paylaşacağım ekranı. Görülüyor sanırım ekran. Okay. And while now we are continuing the pseudocode. This is just the end of the while loop. Position is equal to left, and low is equal to L position, and L position is equal to X. Correct position of the pivot element. Let me remark here. And then end. Okay. So we already mentioned some other alternatives in the literature. Select the pivot element, like selecting it randomly. And our desire is that if we select a good pivot, then the algorithm will divide the list more or less equally. Okay. We don't want one half to be very skewed in that direction. Okay. And then we call this recursively the function. So we want a more balanced partition. So that's why median works better in practice, actually, because by definition, median divides it balancedly, in a balanced way. So the basic operation is indeed here, while until L right, let me, these comparisons, okay? Because we constantly compare the elements that are pointed to by left and right with the value of the pivot. So these are the basic operations. Comparisons between list elements. And the rearrange module. So if we look at the rearrange here, we say that its right is, it proceeds as long as right is less than left, okay? So it's something like, if this is right and this is left, then it will proceed one more, okay? One more here, one more direction once, and the other also simultaneously in the other direction. So until coming to this, where they are all consecutive, I have high minus low plus 1 steps, right? Because this is low, this is high. I have high minus low plus 1 steps. But because still right is less than left in this direction, I will go 1 step more. So it makes high minus low plus 2. Okay? So this while loop operates for a high minus low plus 2 times. Okay? Efendim, şunu yine yapmam. Tamam. rearrange module always performs high minus low plus 2 operations. Okay. So the best case is if in all iterations the list is divided into 2, equally 2, then we have the best case because we have the less number of iterations. Okay, it's like the binary tree, its height does not increase a lot. Okay, best case. So assume for simplicity that it is equal to n is 2 to the power k minus 1. Okay. So let's think about it for k is equal to 4, L1 to 15. It's L1, 7 and 9, 15, because now the medium one will be index 8. Okay. So if it's like that, so to pivot, and then again, by luck, in each iteration, it's divided into equal parts. Okay, this is the best case. If I divide it into 2 now, but in L1, 7, I have a more skewed distribution. If the variance between the lengths of the 2 parts is a lot, then I'm still not in the best case. So I have to be really lucky to be in the best case. Okay, in all the iterations, I have that. So it's L1, 3, which is of size 3, again 5, 7, which is of size 3 again. In here also 9, 11, and this is 13, 15. Okay, and then I will continue dividing. This will be L1, 1, and this is 3, 3, and I have only one element. 5, 5, 7, 7, 9, 9, 11, 13, 15. Okay. So the smaller the depth of this tree is, the less number of comparisons we have. So in rearrange, always high minus low plus 2 comparisons will be performed. So since in this example n is 2 to the power k minus 1, then the tree has k levels. Okay. In k minus 1 of these levels, because I don't have any comparison in the leaves part, in the last level, in k minus 1 of these levels, there are n plus 1 comparisons. So Bn is k minus 1 n plus 1. Which is a theta n log n, for n is 2 to the power k minus 1. But these functions are non-decreasing. And theta invariant. Hence, we can generalize this result for all n. Okay. So the worst case is that it's very unbalanced in its extreme. And this happens in all of the iterations, in all of the recursions levels, okay? So for quick sort, for example, now since I'm in this implementation, since I'm taking the first element as the pivot, then the worst case happens where? If I'm taking the first element as the pivot and I want a very unbalanced sizes, okay, in each recursion. So when does this occur? In quicksort? Yes. One-sided, you mean? Yes, it will be like that. It will be like a list, actually. I mean, like a path. Yes. But when does this happen? What's the nature of the input in such a case? Yes. Not near sorted, already sorted. If it's near sorted, it will be close to that. So I will have still many comparisons, but I'm talking about the exact worst case here. Okay, so if it's already sorted, and since I'm taking the first element as the pivot, I mean, it's the first element and it's already sorted. So I divide it into two parts that are less than that and greater than that, but one part is always empty. Okay? All the rest are on the other part. I do the same, all the rest on the, so, I mean, I have like a path here, not, so it will be like this list, it's, I mean, a path is always a tree, but its height is definitely a lot, okay? The depth of the tree is a lot. So if the list is already sorted, so it becomes equal to linear search. Okay. So it's like L115, and then it will be 215, 315, up until like 1415 or 1515. I don't have any here. So 16 comparisons, 15 minus 1. So worst case, n is equal to I from 3 to n plus 1, I, which is equal to theta n square. Okay? So it starts from 3 to 1, doesn't matter. So it's n square, which is not different from, the complexity is not different from insertion sort. So if my input is already sorted, then there is no point in using quick sort. So if it's close to being sorted, then again, it doesn't make much sense to use quick sort because it's sophisticated and it, I mean, computationally, so it works for inputs that are very distributed in nature in terms of which one is big than that. It's the more far from being sorted it is, the better quicksort becomes. Okay, so how can I measure without making this sorting? How can I measure from first hand, I mean even before starting sorting, that it's far from being sorted, or how far it is away from being sorted? For that, we will see in the second part of this course. We can use the method of counting the number of inversions, which can be done in linear. I don't remember exactly. Time and log n, I think, and log n time. Yes, and log n time we can count the number of inversions is if two elements, one is less, let's say we want to sort it, right? They may be far away from each other in the list, but if the one that has the smaller index has value 2, for example, and the one that has the larger index has value 5, then it's okay. According to, with respect to their relatively to their positions, they are in correct order. So this is not an inversion. But if the one that has the smaller index is 5, but the one that has the larger index is 2, then there is an inversion between these two, right? Because this one should come before the other one, irrespective of what I have in between. Okay, so this is called an inversion. And actually in quicksort, when we make the swap operation, we fix an inversion, at least one inversion. So I may, while doing the swap, I may be automatically fixing other inversions in between too. Okay, so if this is 5 and this is 2 and I have 3 in between, okay, and if I switch 2 and 5, so it becomes automatically 2, 3, 5. So the inversion between 3 and 2 may also get fixed when I do this swap operation. So if I find a way of finding the maximum possible number of inversions, we will see that it's actually nn minus 1 over 2. Everything is an inversion, which means the list is reversely sorted. Then if I count the number of inversions and follow a metric saying that, okay, if this is larger than that or close to that, then it's close to being sorted, or close to being very unsorted, let's say close to having the highest number of inversions. Then let's use quicksort, and other than that, let's use this. For instance, for small input sizes of less than 10, actually, we know that insertion sort works better than the others. This was also shown. So in your coding, for example, this is just, I mean, sorting, you don't do it in actual coding nowadays. Of course, you just call the sort function from Java and you don't care how it handles it. But the reason that we're saying is that this way of thinking is with everything else. I mean, sorting or searching was the foundation of all of this. Once you understand this level of way of thinking, analyzing, okay, analytically, then you can apply the same approach to unknown scenarios that you may have. For instance, with interviews from international companies, I know that they have like 5, 6 levels of interviews, and for some people this is strange and it doesn't make sense, but for some it makes a lot of sense. They ask a lot of questions from data structures and algorithm, even though in some cases the work that you will do will be nothing related to algorithms. For that, I know, and I think this is starting in Turkey as well. So this way of thinking, you apply the same thing for other problems that you encounter in practice. So this is theta n squared. I know that because my husband took one of the interviews because he forgot algorithms after 20 years from graduating. He couldn't pass any one of them. So average case analysis is, of course, as you would expect, is a little bit more difficult, but it's not that difficult. That, for instance, the average case of binary search, if you want to make a precise analysis, then you see, okay, it's binary search. But if you want to make a precise analysis, it may become very dirty, let's say, and complicated. But with quicksort, because quicksort is much more complex to understand than binary search, one thinks that, okay, how complicated the average case can be, but it's not actually. That you will see, it's not very complicated. Of course, when someone gives you the average case, if you didn't know it and if someone asked you, then it might not be that easy to understand. So this is, I would say, not very easy, but medium level. If you concentrate, I think you can understand during the class. For some analysis, you understand it in class, but not 100%. You have to review it from your notes afterwards. Sometimes in class, you understand it immediately and it doesn't matter. This is, I think, with some effort, you can understand in this in the class. And once you review the note, it will be obvious. You won't spend much time. Assume that it is equally likely, as with all average case analysis, that the pivot element which is L low in our implementation will be placed in any position after rearrange. So the proper position of the pivot is important in this algorithm as far as the complexity is concerned. So T can be divided into two terms, like T1 plus T2, where T1 is the number of operations in rearrange, and this is the number of operations in recursive calls. So these T's are random variables, okay? So they are probabilistic values. So we will find their average by n by taking their expectations, okay? By applying the expectation operator. Expected value of T is equal to expected value of T1 plus expected value of T2, okay? So the expected value of T1 is what? In rearrange, I have high minus low plus 2 comparisons, which is n plus 1, okay? Because they become consecutive to each other, and then I make one additional comparison, so that makes actually, this is actually n plus 1. İnternet mi gitti? Durumdayım. Online klasta bağlantı mı gitmiş? Bir sorabilir misiniz?
Hayır
bana
hocam, şu an duyabiliyorum ben sizi. Siz beni duyabiliyor musunuz?
Tamam, güzel. Tamam. Bağlantı gitti dedi de.
Ama bir sesiniz gidip
Depends.
geliyor.
Tamam, onda yapacak bir şey yok. Arada gerçekten gidiyor şu an. Efendim?
Sesiniz çok kesik kesik geliyor arada.
O konuda yapacak bir şey yok. İnternet bağlantısıyla ilgili. Depends on where the pivot has been placed. In that iteration, okay? If proper position of the pivot was L1, then the two sublists are 1, 0, which means empty set, okay, and L2n. So if the proper position of the pivot is L2, then the two sublists are L11 and 3n, which is like one size 1, a list of size 1, and the other one has a list of size 2. Blah, blah, blah. If proper position of the pivot is Li, then the two sublists are L1i minus 1 and Li plus 1 to n, okay? Because the pivot is in I element. Once it's rearranged, I have is index I, the proper position. It means after making the rearrange, okay? It's in the I position of the list after the. So it means it comes from 1 to I minus 1 here. So one of my sublists is from 1 to I minus 1, and the other of my sublists starts from I plus 1 until n. Okay? So that's why it's 1 I plus minus 1 and I plus 1 n. So continue with the two sublists, the size of which depends on how many elements are smaller than that, the sizes. So expected value of T2 is, okay, the pivot can be in any position, right? So that's the position of the pivot is a probability. It's a probabilistic case. So I have to take into account all of these possibilities. Okay, bu arada yoklama kağıdı geçti mi? Tamam, okay. Hatırlatayım dedim. X position of the pivot expected value of T2, given that big X is equal to X. Big X is a random variable that refers to the position of the proper position of the pivot element. If the pivot, the proper position is X times probability that X is equal to X. So in here, we assume equally likely assumption, which means that the pivot can be in any one of these cases with equal probability. And because I have n elements in the list, it's with probability 1 over n, okay? So the probability is 1 over n. So now all I need to do is to calculate this expectation with respect to x, which is the proper position of the pivot element, okay? So an, so because this is 1 over n, an is expected value of T1, which is n plus 1, plus expected value of T2, which is summation I from 1 to n, because the pivot can be in any one of these, okay? 1 to n, the pivot I can be. And expected value of T2, given that x is equal to the position I, times probability that x is equal to I, and this is 1 over n, okay? So this is what? N plus 1 plus summation I from 1 to n. This time I have like, let me show it here. its index I is here, and I have here, I have another average case here from 1 to I minus 1. So this average case in this recursive step is I minus 1, okay? I'm trying to calculate an with respect to input size n. And here in this recursion here, there are two recursions, one here and one here. The average case is I minus 1 because I have I minus 1 elements here, okay? I is the proper position of the pivot element. And in here, the average case is n minus I, okay? Because I is the pivot, I have n. This starts from 1. So this is n minus I, okay? So summation I from 1 to n, I minus 1, because I make both, I run both of them. I sum them up. I'm a plus 1 plus n minus I times 1 over n. 1 over n comes from the equally likely assumption. Okay, so 1 over n, I can take it outside because it doesn't depend on I. So, so what kind of a recurrence do I have now? Okay, I have an here, an here. So this is n plus 1 plus. So how is this? Let's, it starts from A0 plus an, right? And then it's what? A1 plus an minus 1, right? So A2 plus an minus 2, sorry, A0 plus an minus 1, A1 plus an minus 2, A2 plus an minus 3, etc. until an minus 1 plus A0, right? So I actually sum all of these up, okay? I'm talking about what this summation means. I have just written it out explicitly. For I, the first one is I is equal to 1, which makes A0 plus an minus 1, right? The first term. This is for I is equal to 1. This is for I is equal to 2. I have A1 plus an minus 2, right? And this is for I is equal to 3. And then blah, blah, blah. One of them increases by 1 and the other decreases by 1. Until the last is for I is equal to n. For I is equal to n, I have n minus 1 plus A0, right? So now pay attention to the fact that I have two A0s. Okay. I have two A1s, which is one before that. I have two an minus 1, two an minus 2, which will be here. So I have two from each of these. Okay? Because I'm summing them, like I'm coming from left to right and right to left. That's how, because of the rearranged part also. N plus 1. So I have two of these, and in each of them I have 1 over n. So this is actually becomes like 2 over n here, because it's 1 over n plus 1 over n. Okay, 2 over n, A0 plus A1 plus an minus 1. Because I have two from each term. I have 2A0, 2A1, 2an minus 1, okay, times 1 over n in each of them. So I can take it out as 2 over n as this, okay? So this is a special, this has a special nature, let's say, this type of recurrence. And here actually, sorry. Okay. This is, okay, we have seen recurrences like in Fibonacci, for instance. We have seen that it's Fn is Fn minus 1 plus Fn minus 2. So I have 2 units of memory. I just keep track of what happened 2 unit times ago, okay? And then I forget the rest. So this is like the memory in your recursion. But here I don't forget anything. I have like an elephant's memory. I mean, even what's happened, this is called a full history recurrence relation, okay? What happened in each step is important. I don't rely on only what happened 2 iterations ago or 3, even 1 iteration ago. I don't care, okay? I mean, I care to all of them in each time. So this is called full history recurrence relation. And okay, we have time. And now we will solve this, okay? So it looks complicated at first, but it has a very symmetric structure as we had here. I have 2 from each term. So now the trick is I do this. I multiply everything by n, okay? N times an, which becomes what? N times n plus 1, okay? And this n term in the denominator disappears now, plus 2 times a0 plus a1 plus a n minus 1, okay? So, and then I do this. And I write n minus 1 times a n minus 1. So I replace n by n minus 1 and see what happens, okay? This time it becomes n times n minus 1, right? N minus 1 time. I replace n by n minus 1 plus 2 times a0 plus this time until n minus 2, okay? So I see many of the terms that I have already seen. If I subtract these, okay, see what I obtain. It means that, okay, when I subtract, it says that n times an minus n minus 1 times a n minus 1 is equal to what? This is a0 exists, okay? Okay, maybe I shouldn't have, okay, 2 still there. 2a0 minus 2a0, 2a1 minus 2a1. an minus 2 here, the previous term, an minus 2. I only remain with an minus 1, right? In this, right? But here I have what? I have n plus 1 minus n minus 1. It comes from the first terms. Plus I end up with only 2 times a n minus 1, right? 2 times a n minus 1. So this is what? This is n squared plus n minus n squared plus n. This is equal to 2n, okay? So it's what actually? It's 2n plus 2 times a n minus 1. N times an minus n minus 1 times a n minus 1 is equal to this. So it's not very simple yet, but there's hope, okay? Because I have eliminated the full history recurrence and I have expressed n in terms of n minus 1, okay? Everything. I have written it only in terms of like, again, a recurrence type relation, but I don't have the full history now. I mean, I have the full history within the recursion, but I don't have it in the formulation. Of course, it's the same thing. I just made some manipulations, but now I can say that okay, now I divide everything by 1 over n plus 1, okay? Or multiply by 1 over n plus 1. So it means an over n plus 1 minus a n minus 1 over n is equal to 2 over n plus 1. Okay? So this is what? This means that an over n plus 1 is equal to a n minus 1 over n plus 2 over n plus 1. So this is important because now I can express this an over n plus 1 by another term, like change of variable here. Let's write tn is equal to an over n plus 1. Okay? So it means that this means that Tn is equal to Tn minus 1 plus 2 over n plus 1, right? Now it's just the first order recurrence relation. Okay? So I can solve it because it's a first order recurrence relation. I can solve it. So A1, so Tn, so A1 is 0, initial conditions. And T0 is equal to A0 over 1, which is 0. Okay. By backward substitution, Tn is equal to summation I from 2 to n, 2 over I plus 1, which is equal to the harmonic series 2 times h n plus 1 minus 3, okay? Because I start from I is equal to 2. Of course, minus 3 will not matter in the complexity analysis. It's 2 times h n plus 1 minus 3. That's what Tn is. So An, so this is the harmonic series that we have also seen previously. Harmonic series. Because An is equal to Tn times n plus 1. So this is equal to 2 times n plus 1 times h n plus 1 minus 3 times n plus 1. Because this is like ln n plus 1. It's theta n log n, okay? So because hn is logarithmic n, hn plus 1, logarithmic n, and I have n here, and the minus term doesn't matter, I have n log n in the average case. So average and best case complexities of quicksort are very close to each other. And some analysis actually in the literature just showed that An, the average case complexity, is approximately 1.38 of best case complexity. There's just a constant, I mean, both are in the same complexity class, but there's even approximately a constant relation between the two. So it means that in quicksort, on the average, we are very close to the best case. So that's also one of the reasons why it's a pretty good algorithm. Because sometimes we have seen that average case is like the same as worst case. Okay? So even in its own theoretical bounds, it's a good algorithm. Okay, so tomorrow I think we will continue with maximum minimum. Okay, maybe I won't do that. Maybe I will. I don't know. I haven't decided yet. But I will talk about the graph search and traversal algorithms a little bit. And if time permits, and I think it seems that it will, we will start the second part of the course. Okay. The class is over. Okay. Bye, guys.
İyi günler hocam.
İyi günler.
Kolay gelsin.
Sağ olun.